12,000 families, over 1,500 college students and STEM professionals. One thing that I'm proud to say is that we've put over $1 million in the hands of college students over the last 7 years serving as college interns with STEM NOLA, going out and engaging the community. So thank you for tuning in. Parents, thank you for believing in STEM NOLA and trusting us with your most prized possession, your child, your scholar. STEM NOLA believe that either we're training ourselves from the neck up or the neck down. In the 21st century, our children will only have one or three options. Either they're gonna take something, break something, and/or make something. And if we don't give them the skills and education to make something, like make a living, make a life, make a difference, it only leaves them with the two options that we see on the news every night, and that's to take and break. I don't want that for my two children, and I know you don't want that for yours, and that's why we're here today to expose our children to the possibilities of the 21st century. This is my friend. This is Alpha. Alpha is a humanoid. A humanoid is a robot that tries to act like a human. This humanoid has 9 servos and can do pretty much anything physically that a human can do. This is our competitor in the 21st century. Alpha can actually do push-ups. Alpha can even show off. And Alpha can even dance. And like any superhero, Alpha has her own music. This is the machine. And the automatic machine in the 21st century will displace many workers. In the aftermath of COVID, you have to believe that there are many companies out there saying never again will we allow a pandemic or something that happened in nature shut us down. So COVID has exacerbated the possibilities of machines displacing people. If you're competing against Alpha, you will not win. The only way we defeat Alpha is by developing our heart and developing our head, training ourselves from the neck up such that we can control the robots so that the robots will not control us. That's why we're here. That's why STEM NOLA exists. That's why your parents want to make sure that you all participate in events like this so you can know the possibilities of the 21st century. Again, I'm Dr. Kelvin Mackey, and I want to say thank you for tuning in. Now let's get busy innovating, creating, and making with STEM NOLA. Thank you.
All right, thank you, Dr. Mackey, for that amazing introduction. Good afternoon, everyone. I am Keivondra Collins, and I will be your presenter today. Now I'm going to hand it off to our professional volunteer, Z. Smith.
I'll introduce myself a little bit and then set up the conversation for the fun part of all the experiments coming and try to connect buoyancy and density to things that matter to people in New Orleans and Louisiana and really around the world. Just to introduce myself, I grew up in the farm fields of Michigan and Illinois. I studied physics at MIT, electrical engineering and computer science at Princeton, and I have a master's degree in architecture from University of California, Berkeley. Today I work in New Orleans at Eskew, Dumez, Ripple. We're a roughly 50-person architecture firm. And some of my fellow colleagues here from EDR, Will Netter here, and Rylan Auburn have presented at other sessions for STEM NOLA. So I want to talk about density and buoyancy. So just to go over what's density. Density is kind of how much you have in a given amount of volume. And so if we think about this just to kind of illustrate the spectrum, imagine I had a cube. It's 1 foot tall, 1 foot wide, 1 foot deep. And that cube could be of air, of styrofoam, of wood, of water, of concrete, of steel, or of gold. Well, how much would that cubic foot weigh? Well, if it's air, it's less than 1/10 of a pound. Styrofoam is 3 pounds, easy to pick up and toss around. Wood, 26 pounds. If you're in good shape, you can do it. Water, that cubic foot is 64 pounds. concrete 146 pounds, steel 490 pounds, and gold 1,206 pounds. Well, that's each of these was a cubic foot. And what we mean by density is we just say for that cubic foot, here's the weight and here's the amount of volume. So that's the same thing as that wood is 26 pounds per cubic foot, or water is 64 pounds per cubic foot. That's the typical way that we talk about density, is the mass, or here on Earth, the weight divided by the volume. So easy to remember things. If I have a solid chunk of something, if its density is less than water, then it'll float. So, styrofoam at 3 pounds per cubic foot, it's a lot lower density than water. So yeah, it'll float. In fact, it mostly floats above water. On the other hand, wood is 26 pounds per cubic foot. It's about half the density of water. So a log you'll see floating in the water will typically be about half submerged. An iceberg, right? Ice is just a little bit less dense than water. Like it's a little like 10% less dense than water. So that's the source of that whole idea that an iceberg, you only see the 10% above the water that's floating, that there's this huge thing lurking below water. Now, in school, we're often talked about this famous Greek guy, Archimedes, who used density in a really interesting way. He worked for this king, and the king said, my goldsmith, I gave him this big chunk of gold to make my fancy crown, but I'm wondering whether he really used all the gold to make my crown. I know how much my crown weighs. It weighs the same amount, but I'm wondering if what he did was he mixed some, like maybe a quarter of that with some silver that's a lot cheaper, and kept that gold for himself. I want to know, did he cheat me or not? And so Archimedes goes, well, simple. Let's melt down that crown, and we'll measure how much its volume is. We know its density, and we know what the density of gold is. And the king goes, no, but I like my crown. It's really beautiful. So can't you find a way to test how much volume is in there, what the density of this crown is, without destroying it? And so Archimedes, I didn't know what to do, didn't want what to do, decided I need to think clearly. Maybe I'll take a bath. So he's lowering himself down into the bath, and he notices the water rises up as he lowers himself into the bath. And that's when he said, he spoke in Greek because he was Archimedes, he said, Eureka. And all Eureka means is, I've found it, I found the answer. And the answer is that the amount of volume, no matter how crazy the shape of Archimedes or the crown, will be found by the volume of water that's displaced, meaning pushed out. So if you take a big cup of water and you fill it up right to the brim, and then you take some oddly shaped thing, in this case, a little tiny pear, and you push it down in the water, the volume of that pear is exactly the quantity of water that spills out the brim. And you can measure the volume of water that fell into that tray, or you can measure the weight of the water and just weigh it. Either way, because we know that the density of water is 64 pounds per cubic feet, you can measure the weight or you can measure the volume. Either way, you can tell exactly how much water came out, and therefore what the volume was of that object. So wait a second, you said that things that were less dense than water float, but we know that steel is a lot more dense than water. So why don't boats sink? Well, the answer is boats aren't solid steel. If a boat was filled with steel, it would sink like a rock. Instead, boat has a steel shell and then a lot of air. And so you need the total weight and the total volume gives you a density. And the air weighs a lot less than water, is a lot less dense than water. So the combination of the air and steel makes something that is less dense. And the neat trick is, if you want to know how high or low the boat will flow in the water, it's that if you take the volume of the water, the weight of the water that gets displaced as you put the boat in the water, that's identically equal to how much that boat weighs. So how does that apply to life today? Well, here in Louisiana, we live a lot on the water, and there are all these great houseboats that are often towed we build them on land, we put them in the water, and we tow them to where we'd like to go, live in the bayou, do some great fishing. And these can get pretty fancy. With 2 stories, you can have a deck, all kinds of things. In the Netherlands, which is a whole country where half the whole country is below sea level, everyone loves living on the water, but of course they're on the ocean, and so tides go up and down. So what they've done is they've developed a form of housing that there's these piers going down into the mud below the water, and then the whole boat goes up and down with the tide as the tide comes in and out. But we have another thing of concern with climate change. We're all concerned about bigger and bigger storms. And so during those storms, most of the time, it's going to be completely dry, but occasionally there might be flooding events. So rather than the flooding coming in and doing damage to our house, or having to make our house be up high in the air most of the time when we don't want to live high up in the air most of the time, what if we could make our houses, they could be kind of amphibious, right? A frog is an amphibian. He spends part of his life in the water, part of his life on the land. What if our houses could be amphibious? And so there's a whole project being done for all kinds of different countries, different parts of America and around the world, to make houses that can float, that can be amphibious. Led by this project called the Buoyant Foundation Project that Elizabeth English drives. But we've already built some examples of these buildings. So here in New Orleans, there's this building called the Float House. It's built as part of the Make It Right Foundation, where this is a bunch of college kids, and they got together and they get these big honking chunks of styrofoam, and they drill out, they put all the power lines and the sewer lines and the water lines into that styrofoam, and then they spray on some thin, super thin concrete around it. And now you've got this floating object that's like incredibly strong. They put it on the back of a truck. They did this they were in Los Angeles. They drove it across the country. Here they are driving it right past the Superdome. They crane it into place and they build the house right on top. And so now you have a house that can float, but during normal times, it can look like any other house just sitting right on the ground. So these are the ideas of how buoyancy and density show up in our lives in lots of different ways. So with that introduction.
All right, thank you, Z. Smith. That was a very informative presentation on buoyancy and density. Okay, so now we're gonna go ahead and jump right into our activities for today. All right, so on the agenda, guys, we're gonna first go over our vocabulary words, and then we're gonna go over our objectives and our activity questions. For our activities, we are gonna be doing a clay boat and a floating oranges challenge. And then lastly, we're gonna go over our activity questions and answers, and then some Q&A questions and answers that you guys can ask me at the end. All right, so let's begin. All right, so here are our vocabulary words. The first word is density. Density is how close together the molecules of a substance are, or how much mass a substance has in a given space. Buoyancy. Buoyancy is the upward force that a fluid exerts on an object less than itself. Water displacement. It occurs when an object is largely immersed in fluid, pushing it out of the way and taking its place. And lastly, Archimedes Principles. It states that the weight of an object submerged in fluid is also equal to the weight of the displaced fluid. So for our objectives of today, we will learn the meaning of the terms density, buoyancy, water, displacement, and Archimedes Principle, and we're going to also apply that to the project correctly. You are going to be examining floating oranges as well as making a clay boat. So for our questions of today, I want you guys to keep this on your brain as we're going through our activities. First question is, what is buoyancy? Then we have, what happens when an object is less dense than the water that it is in? And lastly, we have, what happens when an object is more dense than the water that it is in? All right, so for our first activity of today, we're going to be doing clay boat. So before we get started, guys, I want you to go ahead and grab all of your materials. The only materials that you will be needing are clay, water, and a container. So while you guys are going to go ahead and grab your materials, I'll go ahead and explain what we're doing today. So with the clay boat, there's a clay ball and it's also placed in water. It's displaced or it pushes aside the water. So whether the clay will be buoyant or float is determined by Archimedes Principle. All right, and so that states that an object in the fluid is displaced by an object, and it is actually equal to the weight of that fluid that is displaced by. All right, so when that clay is placed in the water, there are two main forces that are working upon the opposite directions. Those two main forces are gravitational force, and the gravitational force is what's pulling the clay downward. And also, we also have the buoyant force, which is pushing the clay upward. All right, so gravity is pulling the clay down. And so with an equal weight of the clay. And while the buoyant force is pushing the clay upward with an equal force of the weight of the water. All right. All right, so if the clay is displaced, a volume of the water that is equal to it, then the weight of the clay will be buoyant and it will float. All right, guys, so let's get started. So once you have all of your materials, all right, we're gonna first go ahead and grab our clay. All right, so I'm gonna put on some gloves for this one. All right, and so go ahead and grab your clay. You want to scoop out a ball. All right. So I've got me a little ball. I'm going to grab a little bit more of clay. All right. All right, so once you grab and have your ball of clay, I want you to mold it into the shape of a ball, okay? All right. So I want you guys to ask yourself, can a ball of clay float? Does anyone know if a ball of clay can float? All right, so we're about to see if that is true or not right now. So now, guys, with your container, go ahead and fill it up with water. All right, so we're gonna go ahead and pour water into our container. You don't have to fill it up all the way to the top. You can fill it up about halfway, and that should be good enough. All right. Now, guys, with that ball of clay that we just made, go ahead and drop it in the water and let me know what you see. Okay, so now that we've tested it, we now know that a ball of clay will definitely sink to the bottom. All right, so now let's see and test it out if we can flatten the ball, and let's see if it'll sink again. Let's flatten it. All right, so you can go ahead and just push it together. Make it as flat as you can. All right, so what we're doing here, guys, we're molding our clay and we're making it a lot less dense than before. Let's see if this affects it. All right, so now I have a flat piece of clay. I'm gonna drop it in the water again and let's see what happens. It sinks. Okay, let's see. Do we think that we can change the shape of it to get it to float? So let's see. I'm gonna try and bend and mold my clay into the shape of a boat. All right. So my clay is a little wet, but I think I can mold it into a little boat shape. So what you want to do is you want to pinch the edges of your clay. And we're kind of hollowing out the shape of our clay. And you may need to take away some of the clay just to make it a little lighter, all right? All right, so now I'm gonna take away like about half of the clay just to see if that'll change the outcome. All right, so go ahead. I'm gonna go ahead and reshape my clay first and flatten it out. And then form my boat shape. All right, and you can do that by pressing your thumb in the center and pinching the edges upward. It's not a perfect boat, but you guys see what I have here. Let's see if we'll have a different outcome. Okay. I'm gonna try it out. Oh no, our boat sunk again. Okay, so let's see what we can do to fix that. We may need to take away some of the clay or just grab some more clay because also our clay has been affected by the water. So I'm gonna grab some dry clay and test it out again. All right, so I'm gonna scoop up some dry clay. This time I'm grabbing less clay than before. All right, I'm gonna ball it up. So guys, have you ever wondered what makes a boat float in water? A boat is really, really heavy, but yet it seems to float in water. So guys, the reason for that is because of the amount of air that is inside the bottom of the boat. It actually allows for it to float in water, being that it's hollow on the inside and there's less air in the boat than there is water surrounding the boat. All right, so now I'm gonna go ahead and take my new clay boat and try it out again. This time I'm gonna flatten out the edges a little more. All right. I'm gonna curl the edges up a bit. Let's see what happens. So I think the reason why my boat keeps sinking is because my edges are not curled up enough. All right. Let's try it out with some different clay this time. All right, so now I'm gonna switch gears and try out a new set of clay, all right? As that other clay was getting a bit messy. All right, let's see what we'll have with this clay here. All right, so I'm gonna take a little bit out. All right, so I have the clay. All right, I'm gonna try it again. I'm gonna mold my ball, roll it up, press it flat. All right. And now curl the edges up. All right, now let's test our boat out. Let's see what happens. Voila! Yay, so our boat has now floated. Okay, so notice that the different shapes that we tried before were sinking. So a shape that is a lot more hollow on the inside where there's more air will allow for it to float above the water. And this is due to water displacement. All right, guys. So I'm gonna go ahead and clean up my station and we're gonna go ahead and move on to our next activity, okay? All right, guys. So now we're going to move on to our next activity. And this one is called floating oranges. Okay, so for floating oranges, you're going to only need 2 oranges, 2 cups or 2 glass containers, and water. All right, so a little bit about what we're about to experiment with here. We're going to be learning about density. So density is the amount of matter that will fit in a given space. Buoyancy relates to the object's ability to sink or float. So the orange pill is going to float, or the orange with the pill is going to float. Because the pill is very porous and it's filled with little air pockets. Those air pockets actually help to increase the buoyancy of the orange. So this increased buoyancy helps the orange to become less dense and than the water. And so the orange will float in the water. And so you want to think of those air pockets in the orange peel as like tiny flotation devices for the orange itself. But on the flip side, on the other hand, when you remove this pill from the orange, you are going to, in fact, make it lighter. However, you're going to also remove those tiny flotation devices, those air pockets that are in the actual pill. So therefore, the orange pill or the orange without the pill is going to be denser than the water, and it's going to cause it to sink. So buoyancy is the tendency of an object being able to float in fluids because of the upward force that is exerted on the objects in the fluid. All right, so let's move on. All right. So first, I have my 2 glasses here. And I have my water, and I also have my oranges. All right, so I'm gonna fill up both my glasses with equal amounts of water. I think that's enough. I think that's about equal. There we go. All right, so now I'm gonna go ahead and grab 2 oranges that are about identical in size. I think these 2 are perfect. All right, so with 1 orange, I'm going to drop one in one glass container, and then the other, I'm gonna drop it in the other. So with this orange, I'm gonna go ahead and peel the peel off first. So remember, guys, when I was reading to you guys about what's gonna take place, remember those air pockets are gonna be very key in this actual experiment. All right, so now I have peeled the peel off of one of my oranges, and the other orange here has the peel on. So I'm gonna go ahead and drop them both in the water at the same time, and let's see what happens. Oh, I know why this one floated. So if you aren't very careful and if you poke a hole through it, it could float, being that you just created a little air pocket for water to enter. So I'm going to start over. I'm going to take another orange and try to re-peel it and see what happens. This time I'll be a lot more careful as I'm peeling. So be a little gentle with this orange as you're peeling. Keep in mind that a hole could rip through. Ooh, oh no, I ended up breaking mine. Don't do what I did. One of the halves. Okay, let's see. Okay. So we see part of this orange is hovering in the water, whereas this orange here is floating above the water. So now we see the difference. The air pockets in this orange is helping it to stay afloat above the water, whereas this orange, it is a bit sunken, as you can see, under the water line.
So even though the peeled one is definitely lighter, the other one floats better.
So even though this peeled one here is definitely a lot lighter than the one with the peel, because this one has the peel with the porous air pockets, it allows it to float above the water, whereas this one that is lighter still is sinking a lot lower. And that's because it does not have porous air pockets around it to keep it afloat. Isn't that fascinating, guys? All right. So that concludes our activities. So now we're going to hop right back into our questions of the day. All right. So does anyone remember what is buoyancy? Also, what happens when an object is less dense than the water that it's in? And I want you to answer the last question that says, what happens when an object is more dense than the water that it's in? All right. All right. I think all of the answers are in. All right, guys, give yourself a pat on the back if you've gotten all 3 questions correctly. Obviously, buoyancy is the tendency for an object to float or sink in water. And also an object that is less dense than the water that it's in is more likely to float in water, whereas an object that is more dense than the water that it's in will be more likely to sink in water. All right. Good job, everyone. Thank you for joining me today. As always, go ahead and share your images and pictures to webinar@stemnola.com. And please join us again for our next STEM at Home activity that we're going to be having on Thursday, November 18th. Bye, everyone.